Dear Professor and fellow students, first of all, I need to mention that this presentation is for the International Conference on Internet Technology and Secure Transaction. Now please let me introduce myself. My name is Liu Juhua from Tsinghua University of China. Today I'm going to present my paper titled by Efficient Hardware Implementation of ITUbee based on composite field. I will talk about three aspects. The first one is the description of ITUbee. The second one is the hardware implementation of ITUbee. The last one is implementation results. ITUbee is a lightweight cryptography algorithm which is published on LastStack 2013. The purpose for designing this algorithm is to have high software performance, namely low energy consumption and low memory usage. However, because of its physical structure and iterative module, this algorithm is potentially suitable for efficient hardware implementation. Since there is no hardware implementation for this algorithm before, in this paper, we present a low-area hardware implementation for ITUbee. Now let's look at the structure of ITUbee. On the picture of the left, you can see that the ITUbee applies a physical structure. That is to say, the input is divided into two branches. After going through the round function, the left part XOR the right part. And the block size for this algorithm is 80 bits. The key size is also 80 bits. However, what I want you guys to notice most is the f function. The f function is used two times. You can see here, two times in the round function. And for your information, the f function is the most complicated part. It consists of two S boxes and one L layer. And the S boxes used here is the same as in AES. In order to optimize the area resources, we figured out two critical points. The first point is that we can use serialized architecture to implement one round. In this way, we can just reuse some iterative module. The second point is that we implemented the S-box using composite fields. Compared to the traditional looking up tables, this way is way more efficient on area consumption. First, let's talk about the implementation of S-box. You can see in the value table of S-box, the input-output relationship is complicated. Normally, there are two ways to implement this S-box. One is to use lookup table. That is just to give all the possibilities for input and output. Another way is to use mathematical methods. Since the S-box function can be defined in this way. It is defined by two sub-steps. The first sub-step is to get the multiplicative inverse of a of A in the field of a's power of 2. And then the second sub-step is to do a fan transformation like this. Before I go further, I need to give a few preliminary knowledge about the composite fields. As we know, there is a irreducible polynomial qs equals to h power of x plus fourth power of x plus third power of x plus x and 1. If a Now let's say J is an element in the field of its power of 2, this field. If A is the root of Qx, then the Pauli basis is a form like this, and the normal basis is a form like this. The elements in this field, in the field of s power of 2, can be represented either by using Pauli basis or normal basis. The relationship between different representative is this formula. Here X is a converting matrix. We call that J and J prime is isomorphic. Then is the subfield theory. Let's say if K equals Mn, then this field is the subfield of this field. Of course, you can see that. For example, when we give a 2-degree irreducible polynomial, like this one, we can represent the element j of jf its power of 2 and a linear polynomial over this field. Here, the pair y and 1 is the polynomial basis. In a similar way, we can also use normal basis to pair this and this. Of course, they can also represent an element of jf fourth power of 2 over jf second power of 2. Now here's the hierarchy structure. First, since the element in S-box is represented by the form of Pauli basis, we need to use a isomorphism matrix to transform the input to represent the input by the form of a normal basis. Then we use the subfield theory to get the multiplicative inversion in GF s power of 2. After that, we can use another isomorphism matrix to transform it back to the form of Pauli basis. Then we apply a fan transformation to the data to get the output. Here are the representation in subfields. For example, when we want to represent an element in this field over this field, we can choose normal basis to pair 16 power of y and y. Then the element in this field can be represented in this way. It's similar to the field of first power of 2 and second power of 2. Now we need to know that how to get the multiplicative inversion in the field of s power of 2. According to the multiplicative inversion definition, the formula for them is this one. When expressed in the float chart, it's like this. So we can divide the inverter in the field of s power of 2 into many different operations of like addition, multiplication, inverter, squaring, then scaling in the subfield fourth power of 2. Similarly, we can also divide the operation in the field of fourth power of 2 into different operations in the next subfield level. Here is like this, etc. Similarly and similarly until we divided the operation into this field. It's like the last subfield. And in this field, the multiplication just means and plus means XOR. For changes of different representatives, we need a transformation matrix, and the change of basis matrix for the best case is this one. Now it's come to the serialized architecture for ITUbee implementation, and I have mentioned before, the f function is used 2 times in one round, so we use 2 cycles to implement this 2 times. In this way, f function only need to be written one time on hardware, as you can see in the path. Of course, the disadvantage is that it costs one more 40-bit register and some multiplexers, because we need to make more branches and need one more register to save the intermediate data. Here we give the implementation results and comparisons between different schemes. First, when we use the composite field to implement SBox, 346.6 GE is used. When using looking up tables, 543.8 GE is used. By comparison, the composite field we can save about 32.7% in each 8 S boxes. Second, when we reuse the f function, the whole algorithm costs like 6,448 GE. If we don't reuse the f function, the whole algorithm costs 9,812 GE. By comparison, the reusing scheme can save area by about 31% 0.2%. Now we reach a conclusion in this paper. We proposed an efficient hardware implementation for ITUbee. The composite fields arithmetic and serialized architecture can effectively improve the hardware performance. Thanks. If you have any question, please just send me an email.